Okay, so I apologize. I think something happened at the end of the first segment of section 2.4. I stopped somewhere around here, and the Zoom connection got cut off and the recording stopped. So here's the continuation, or the second part, the brief part of section 2.4 on continuity. I have given you, well, first I gave you the definition of a continuous function at a point. And now we have just defined what it means for the function to be continuous on an interval. Basically, it just means it's continuous at every point on that interval. All right, so that is, that's an easy to understand definition. And I'm going to give you some examples. There are lots of examples. In fact, most of the functions you have ever studied in your life, in all of your mathematics classes up to this point, are probably continuous at most places. All right, so polynomial, remember polynomial functions are nice, polynomial functions, polynomials. And that's because they are all continuous everywhere, okay? And then you have sine and cosine function. These are defined for all real numbers. And remember how smooth and continuous those functions are at every single point. All right, and then you have exponential functions. What are those? Like e to the x, 10 to the x, whatever. Okay, these are functions that are defined at every single point. So these are all continuous on the entire interval from negative infinity to positive infinity. In other words, on the entire real line. Okay, now some other functions are not defined on the entire line, like log functions. All right, you remember log functions like natural log of x, the common log of x. Okay, these are continuous wherever it's defined. What does that mean? Well, the domain is from 0 to infinity, not including 0. And then we had rational functions. These are polynomial over polynomials. And you say, well, these are not continuous. Right, because they have vertical asymptotes, right? But those are precisely the points where the rational functions are not defined. So if you look at every point where a rational function is defined, the function is actually continuous at that point, right? So rational functions, root functions are not defined at every single point, like the square root is only defined for non-negative numbers, right? And then other trig functions, these are like tangent, cotangent, secant and cosecant. These are not defined at every single point. And again, they have vertical asymptotes. But at every single point where these are defined, the function is continuous. All right, so pretty much everything you have studied, okay, these are all continuous functions. We say these are continuous on the domain. On the entire domain of, in other words, every point of the domain, the function is continuous, all right? So that gives you a wide range of and a variety of functions that are all continuous wherever they are defined. All right, we have a couple of theorems about continuity and continuous functions, and they will help you tremendously as you find limits and as you decide on where the function is continuous or discontinuous. All right, so the first statement is this. If you have two functions, f and g, which are both continuous at a point A, then you can get a whole bunch of other functions that are continuous. So are the sum of the two functions, the difference of two functions, a constant multiple of a function, the product of these two functions, and the fraction or the quotient of f by g, unless, of course, g of a is equal to 0, then of course you lose the continuity because you have 0 denominator. Okay, so that gives you a lot of things that are, and by the way, k here is a constant. Okay, a constant multiple of a continuous function is also continuous. All right, and the second one, maybe I should move this up a little bit. I think I can do this, can I? Yep, okay, so I'll move this up a little bit because I want to write something below this. If g Okay, so let me illustrate. If G is continuous at A, and when that produces G of A, which is now thrown into a new function F, the second function, and now of course I'm talking about the composition of two functions. If A is continuous at this new input called G of A, then remember F of G, the composition of these two functions, that's F of G, is continuous at the input value of A. So the composition of two functions happens to be continuous as well. Okay, so this gives you lots of different functions. Let me give you an example. You remember we looked at this problem, x squared sine of 1 over x. All right, so the sine of 1 over x, okay, this is that weird function that goes up and down, the one that the sin function, sin, the sin function, it goes crazy around the origin. And but that's okay. You know that this function here, 1 over x, that's a rational function. So according to that, remember it is continuous everywhere it's defined. So this is continuous. 1 over x is continuous except at 0. No problem, right? It's the only point. X is equal to 0 is the only point where 1 over x is not continuous because you have that vertical asymptote and the function is not defined. Sine is a continuous function. So now here we have a composition of two functions, the reciprocal function followed by the sine function. And because it's a composition of two continuous functions at any non-zero point x, this composition is continuous at every point x where the sine of 1 over x is defined. X squared is a polynomial. It's defined and is continuous everywhere. The composition, not the composition, the product of these two continuous functions is also continuous. And therefore, this entire function f is continuous at all points except at x is equal to 0, where the function is not defined. Right, so this is a result of this continuity for this function is a result of these statements that we have listed as theorems. Okay, so that's kind of nice. It's nice to know that many functions are continuous. All right, finally, we go to the last statement of this section, which is the intermediate value theorem, IVT. Okay, and the name actually makes sense once you understand this. Here's a picture that illustrates this theorem. I'm going to write the statement here in a moment, but imagine this function or look at this function f, which is defined at A, defined at B. So you have FA and FB. These are two different values on Y. And then, okay, so maybe I should write this much down. If F is continuous on this entire interval, including the endpoints A and B, okay, it's closed, it's continuous on the closed interval AB. And if Z is any point, you see this Z, the horizontal line? So this Z happens to be between FA and FB, right? So if Z is any point between, I'm referring to the Y value, between F of A and F of B. Now in this picture, F of A is less than F of B, but it doesn't matter. F could be going down where F of A is bigger than F of B. But however, F is defined. If you pick a point Z between FA and FB, then there is at least one point. You can also say there is a point, but it's more mathematically precise if you say there is at least one point C on this interval, and in fact, it's going to be an open interval, such that, okay, ST means such that, okay, F of C is equal to Z. And you can see this point C. Okay, I have randomly chosen Z between F of A and F of B. So this is like any kind of a Y value between F of A and F of B. And so that blue line is going to be crossed by F, the continuous function at this point C. And now you may have several points. You know, if the function is like this, and if you pick z this way, you may have like 3 points where f of c is equal to z, right? But the intermediate value theorem guarantees at least 1 point c, so that f of c is the value given as the intermediate value z. Okay, now that's, is this surprising? How can the function f not cross an intermediate value? Okay, in other words, you have f of a here, right? And f of b here, okay? And you're picking an intermediate value, z. So it's like, you know, you have this road, which is this, you know, this wide from f of a to fb, and z is like the center line. Now you have to go across from this side of the road to this side of the road continuously, without jumping or flying or disappearing and appearing on the other side. You of course have to cross the center line or wherever this z is, okay? Here's the point. And so this is intuitively easy to understand if you understand this at all, okay? So the intermediate value theorem says, as long as the function is continuous, okay? If you walk continuously from one side of the road to the other, then you have to go through z. Here's another way to imply this, another implication of this, right? You see South America here, North America here, okay? There are a bunch of these countries between the North and the South America, but the southernmost of the North American countries is Mexico, right? And Mexico goes from the west, this side to this side, right? Now, if you walk from South America to the United States, right? From this side to this side. Now, of course, you have to walk continuously because you're not jumping, you're not flying, you're not disappearing or going to the other side of the earth. If you walk from here to here, you have to go through Mexico. Okay, that is an implication or an application of the intermediate value theorem. Now, you could possibly, if f is not continuous, okay, if you can somehow jump or have a gap, it's possible not to cross z. So look at this picture here. If f is not continuous, like if f goes from here, this is f of a, and then jump from here to this, then you can actually skip this horizontal line z. You're jumping from here to here. Okay, so the fact that f is continuous is actually very important, critical. If f is continuous, you are guaranteed to cross this line z, somewhere between a and b. All right. If you have an asymptote, like here, here's the asymptote. And this is of f of a, this is f of b. And this is the z value, which will not be crossed by this discontinuous function. So again, the fact that f is continuous is important. Okay, no problem here, right? Now you say, well, duh, this is easy. Yeah, of course, if you have to go from this side to the other side, you have to cross the entire road. Yeah, and that easy to understand theorem is called the intermediate value theorem, which is going to be used as we prove certain theorems in calculus in the days to come. All right, one implication, perhaps that would illustrate how meaningful, how reasonable this intermediate value theorem is this fact. Think about this, okay? Think about this in your life, right? You realize there was at least one time when you weighted exactly 50 pounds. Assuming that you now weigh more than 50 pounds. Okay, how so? And why is the intermediate value theorem relevant to this statement? All right, so when you were born, okay, you probably weighed like 7 pounds, 8 pounds, maybe 9 pounds. Maybe you were smaller, 6, 5 pounds. You know, some children are born even with less weight than that. Okay, a typical adult, maybe you weigh like 100 pounds, 150 pounds, 200 pounds. Let's say you were born at 7 pounds and you have grown to be 150 pounds today. This is at birth, this is now. Okay, now we assume that the weight function is continuous because you are not going to jump from 10 pounds in the next moment. You're not going to weigh like 70 pounds, right? So it's continuous. And once you assume the continuity of this weight function, anywhere between 7 and 150, like here's a line of 50. Okay? There was a time in your life where you weighed exactly 50 points. 50 pounds, all right? And also when you weighed 100 pounds or when you weighed 10 pounds, because all of these are intermediate values between 7 and 150. So that's a silly application. Yes, that's true, okay? But remember this as we go into the more advanced theorems of calculus. The IVT will be referred to perhaps several times in this course. So, and that's it. That leads us to the end of chapter section 2.4. And we have one more section left in chapter 2. And that would be on the precise definition of limits. All right, have a wonderful day. I will see you soon.